class. Today we do another experiment. The topic of experiment is a Young double-slit experiment. And this experiment is, again, it can be explained by classical physics. We don't need the quantum mechanics to explain it. In 1800s, one English scientist, Thomas Young, did an experiment, and he proved that light behaves like a wave. Before that, the theory of Newton, the theory that Newton proposed, was dominant, and scientists assumed that the light behaved like the particles. But by his experiment, it was proved that the light behaves like a wave. And because of waves, so we expect interference. They can interfere constructively or destructively. Okay, let me show his experimental setup. Use a light source, ordinary light source. Then he made two holes here, very close together. The distance between these two holes are D. And then, very far distance, he placed a screen. We assume that the distance between the screens and these two sources are much more than the distance between these two slits. Then, if everything is okay, you can see some bright and dark fringes like this. See, this one is the bright, the central is the bright, then dark, bright, dark, and it continues like this. So, as you see, this one is the proof, the real proof that the waves here, they interfere constructively, and here they interfere destructively. So, they cancel out each other. There are some formulas for these you have seen in general physics. Let me refresh your memory. The order of the central, there's a bright is 0, then 1, upward is positive, downward is negative, and for dark is the positive 1/2, negative 1/2. You can continue like this. We have this formula for bright, the position of the bright fringes. You see that? Then is the order R lambda D. The lambda is the wavelength. The thing that is important, I didn't mention, the light source should be monochromatic. You can use the broadband, but if you use the broadband, you see many fringes here. So it's better at the beginning you use the monochromatic. And then this one is therefore the formula for the dark fringes. So in experimental setup that I showed you in another video, use the laser light that emits in the almost red, so it's a monochromatic, and it gives us another advantage because the laser light by itself is a coherent, so we can easily, it's much easier to see the fringes here compared with the broadband light source. So I will show the setup, that how could you place some twists here, and then you see the fringes. We have a detector. Our detector is like this. We use the slit in our setup, and for example, if I place the detector here, what we see that here is a bright fringes. So it means that if I place for example, a slit here, like this, assume that I place a slit like here. So just the light from here can go to the detector, and because the bright, it can produce some signals. So we see something. I will show you, for example, oscilloscope. When I move this, if I place this slit here because there is dark, there is no light, so there is no signal. So it is the way that you can record the bright and dark fringes. You have a slit, and then you move from the dark to bright, from bright to dark, and so on. Then you can record the distance also between these two fringes. The next part, the next section of this experiment, again is interference, but it's a bit different. We call it double slit. We can do the same experiment with the single slit. So we call it a diffraction. Again, diffraction is a type of interference. There is no difference between them. In fact, here we have two distinct sources, but here we have a continuous bunch of sources that are together. Anyway, here this slit or hole should be on the order of the wavelengths. I mean that it shouldn't be too much more than the wavelengths. And again, we have the same setup, R, and then R should be again, of course, R should be much bigger than A. Then again, we see some fringes. It's a bit different. The central fringe is very bright, very big one, that in fact is the image of this. Then we see something here that they decay very fast. So here they decay, but it's very slow. But here it decay very fast. So this one is diffraction, that one is the double slit. And again, we can find another formula for this. N is equal to the same formula, but instead of the D, you see that I replace A. So again, we have the same setup. The only thing that we change, we use the single slit here in our experimental setup, and here we have the double slit that I will explain in the next video for you. So this one is everything that you should know about this